Okay, awesome. So yeah, we have a graph on n vertices. In fact, the graph is complete. It's a kn, which is to say that all vertices, all pairs of vertices are joined together. So this is a K5, for example. Yeah, sorry, this is just a single edge. Yeah, so this is K5. And we color the edges of this graph. Yeah. In such a way that every triangle contains and the number of colors is not, let's say it's n choose 2. Yeah, so there are as many colors as you want, but we won't need more than n choose 2 colors because there are only n choose 2 edges. Yeah, so we color it in such a way that every triangle contains either one color, exactly one color, that is all edges have the same color, or it has exactly 3 colors. And such a graph is called a swell colored graph. Okay. Yeah. So first of all, can KN be spell colored using 2 colors?
No,
Why is that so?
because it two colors means like one triangle should have well, like one there should be a triangle which has both the colors, but there are like it should be three different, but you have only two. So there will be
And
two colors, one triangle.
why should there be a triangle that uses both colors?
Because if there is not, then it will be a swell color with only one color.
Why?
Because like
Uh,
it's a complete graph.
yeah. So how do you prove that if we use both colors, then there must be a triangle using both colors? Because
Like
if
let's
we use
assume that there exists like let there be a vertex V which is
Mhm.
blue and let's say red and blue. Let there be a vertex B which is blue. Then there'll be two other vertices. One of them one of them would be red.
Okay, so note that we're coloring the edges. So I think
Yeah.
I should emphasize this. So we're not coloring the vertices.
Oh.
So it doesn't make sense to say that the vertex is blue. So we're coloring the edges, remember?
So we can like take one edge. Let's say
Okay.
UV is the edge. It's blue,
Mhm. Okay, so
and
let's say it's blue. Yeah.
now if you take any other vertex, all the edges should be blue. Like
Okay.
VW and UW should be blue.
Okay.
And now if you consider any other vertex, let's say X, then VWX should also be blue.
Sure.
Blue triangle. And like in this way you can like form whole the KN graph of it
No,
all.
you can't because these edges are only edges where one of the vertices is adjacent to U and V. So what do you do exactly?
I mean now you consider VXW, no? VX is
Yes.
also
Yes.
there.
Yeah. So in general, if there's any other red edge, then just consider this vertex. I mean, even the previous speaker, I'm not sure who was speaking, but it was the same idea. Yes. Yeah. Your idea works too. Yeah. So if you consider A, then UA and UV must be both blue. But then if you consider VAB, there's a contradiction. because one of them is red and the other is blue. So then there'll be exactly two colors used. Yeah. So of course this is not possible, right? Okay, great. Um, what about three colors? Uh, can KL be swell colored using exactly three colors? In fact, can you find all? Oops, God damn it. Can you find all n for which KN be colored using exactly three colors? Swell
I-
colored using exactly.
Is it all n equal to 3k?
I don't know. You give me a proof of it. Oh, sorry. Yeah.
Okay, I claim the answer is n equal to 3k plus 1.
Okay. But three also works, right? Because certainly blue, red, and white works.
Ah, yes. Okay, hold on.
Hmm. Also, if n does not work, then even n plus one that cannot work, right? Because a if a kn is swell colored, then a kn minus one is also swell colored, right? Any kn minus one. So yeah, I mean, if you can find an n for which it cannot work for that n, then it cannot work for any higher n. So yeah. Okay, so let's think about this. K3 is swell colored, right? Can be swell colored. So equal to 3 works. What about n equal to 4?
And
Can someone provide a swell coloring? I claim that it can be swell colored. Can someone provide me?
so color, let the colors be C1, C2, C3. Let
Let's say
AB,
red, blue, white,
yeah, sure.
if you don't mind. Yeah.
Yeah. AB is red, AC is white,
Okay.
AC is
So
white,
then naturally BC should be blue.
yes. And AD
Mhm.
is blue.
AD is blue.
Now DC
So
is red,
then CD should be red, and then
BD should be
BD
white,
should be white.
yes.
Let's see. Uh, yeah. So all triangles here have three colors. Exactly. There are only four triangles, and we can check that all triangles have three colors. So this works. What about n equal to 5? So let's just try n equal to 5. In fact, I claim that a K5 cannot be spell colored. Can you show this? Again, the answer is no. It cannot be spell colored.
Yeah, from some vertex, some two of them must be the same color.
Okay, so right, because every vertex has a degree 4, so some two have the same color. Let's say it is A, B, C, D, E, and A, B, and A, C have the same color. Naturally, B, C should also have the same color because we are allowed to have one color. But then what next?
Now we consider AD and
Okay.
BC.
AD
Oh,
and BC. Okay.
yeah, okay. So if in triangle ACD three colors are used.
Okay. Let's suppose three colors are used, and without loss of generality, it is this case.
Yes. Now in triangle ABD, can you draw the HBE
Then
in
this
red?
must be red, which is a contradiction
Yes. So
because
we
BCD has exactly two colors. So then this cannot be the case. So then it must be that ACD has only one color, in which case it must be like this. And similarly, even ACE should have that white color. It's symmetric in D and E. Okay,
yes.
what next?
And now BE should also be white and DE should also be white. So there is only one color used.
Good, which is a contradiction. In fact, even BD should be white, then there's a
Yeah.
contradiction. Good. Yeah. So since we cannot spell color 3 swell color n equal to 5, we cannot spell color any n greater than equal to 5, right? Because if we could, then we could just pick a subset of 5 vertices and look at the induced graph there, right? So yes, so there's a question in the chat: if there are k colors, when does it fail? So here's a theorem that I would
Uh,
want you to prove actually, called the Ward-Schwaber theorem. Uh, I don't remember the year, but okay, doesn't matter. So Kn cannot be swell colored with fewer than root n plus 1 colors.
shouldn't you mention like greater than one though? Like one, if you have one
Um,
color, then any n works, no?
yeah, I mean, sure. Yeah, you just manage for large enough n or something. I don't care about that. Maybe say n equal to n is at least um, 3, maybe. Yeah, maybe not even. Yeah, 3, maybe. Yeah.
I had a question.
Yeah.
Does this theorem imply that if you have like more than root n plus 1 colors, then you can like swell color the cane?
It doesn't actually imply it, right? So the converse
Yeah.
isn't true yet. Yes, you're right that we haven't shown that root n plus 1 is the best in some sense. It could be that even root n plus 1 colors isn't enough. But we'll see how that goes. So we know that so for any n, let f of n be the least number of colors needed. Number of colors needed to swell color. Oh, I should also say that we shouldn't use one color or something. Yeah, because that's also spell coloring. Yeah. So I'm not allowed to use one color, let's say, because I could just color everything with the same color. So let's not allow that. Yeah. So least number of colors needed to swell colors Kn. Then I'm saying that Fn is at least root n plus 1. It doesn't exactly say that it's equal to the ceiling of root n plus 1 or something. yet.
Shaurya, in that previous question, I think we can use PHP also, right?
Uh, okay, what's the idea?
Since like from each of the vertices there are four edges which are emerging. So and we have maximum three colors. So at least two of them must be of the same color. And the
Right.
vertices that are joined by these two, the triangle, it has two edges of same color.
But the third could be the same color as well. So there's no contradiction yet. Right? In fact, that's
Yes,
what
so
we
that
did, right?
you cannot use three colors. That's
No, it doesn't exactly show that directly because, for example, we have these five vertices, and let's consider this vertex and say by PHP there are two white edges from it or something. So let's say we have this, and so there is this, but there could be other edges. There are many other edges remaining, right?
oh yes, right.
Which I could,
Oh, okay.
yeah.
So for this, what says whatever
Let's
experiment is?
let's allow other people to think as well.
Sure.
Yeah. Maybe I should add the constraint. I'm not allowed to use exactly one color. So there is some mixture of extremal argument and PHP going on here actually. So Any sort of a progress so far?
Can I see?
Okay.
So by PHP, we have like if we like if let the vertices be C1 to Cn, n plus 1.
Okay.
We take n to be
Uh,
k square first.
sorry. Oh, okay. Sure. Why not? Let's say L is k square for now. Okay. So then your vertices are C1 up to Cn. What
Oh,
is
it's
n plus?
no. Take k square plus 1. Sorry. Yeah. So
Okay.
you have to prove k colors doesn't work.
Sure. Yeah, at most k color doesn't work. Yes. And at
Yeah.
least two. Yeah.
I mean the proof is same even if we show for k colors. We can just generalize it. So
Okay.
by PHP, at least k plus 1 edges from C1 should have the same color.
Why?
I mean,
Doesn't it have degree k square? And if I use k colors, where is the contradiction?
did I
K
take the
square
number?
by k is exactly k. So
I took the
it
number
has
of edges wrong.
like yeah, it's connected. It has k square edges on it. So if there are k colors, why must I have k plus one of some kind?
Sure, like
Uh,
k edges. K edges are all the same color at least, no?
K edges are the same color. Sure.
Yes. So let C1 be connected to like C2, C3, so on till CK plus 1.
Okay. C1, C2 up to CK plus 1 with the
I
same
mean,
color.
it will start from C2, no? C1 is connected.
Oh, yeah. Sorry. Yeah.
So now if you consider any other edge connected with C1, let's say
So these are all
CX.
white. Yeah.
Yes. So let's take CX.
Um, okay. CX. Okay.
And connected with C1.
By what color? Some other color.
Oh yeah, some other color. Let's say it red.
Okay.
Okay, fine. Blue.
Okay. Sure.
Blue works. Fine. So now we consider the triangle C1, CX, CI, where I ranges from 2 to K plus 1.
Okay. Some CI.
Yes. And now note that CIX, the edge CICX, sorry, should be of some
Hmm.
color which is not red and white and which is not covered before.
What do you
I
mean
mean,
before?
okay. So we start from like K plus 1. I goes from K plus 1 to 2.
Okay.
Now, if CK plus 1 CX edges of color blue,
Um, okay.
and now you connect CI CX,
Okay.
it
CK
cannot be
is
blue.
the
I
okay.
mean, consider it.
The one before it is CK.
Yeah, sure.
So it cannot be blue because
CK CX, because if it's blue, then in triangle CK CX CK plus 1, you have two colors.
yes. So then this must be new color. Sure.
Yes. And now, wait a second. I found the number. So yeah, now there is one color red C1 CX, and there are K other colors. So there will be K plus 1 colors needed.
Yes. Okay. Yeah. So these are all distinct colors. Yeah. And that's it, right?
Yeah.
Yeah. So how many colors did you need in fact here?
K plus 1 colors.
Um, uh, I mean, the proof isn't done yet, right?
We used K
I
colors.
guess it is. I guess it is, right?
Yeah.
So,
So now
I
if we
mean,
consider
what if there is no, what if C1, CX is also white?
I mean, then all the C1 CI is white, and then any
Okay,
other edge connecting them is also white. I mean, CI CJ will also be white because of triangle C1 CI CJ.
okay, yeah, that's it, right? Yeah, okay, good. So that's it, right? Is it clear to everyone what happened? Let me know if something's not clear. Okay, it seems it's clear. Okay, good. Yeah, that's it really. And so yeah, so this is pretty much it. And I'll create a problem set where we actually try to show that there are quite a few variables for which this root n plus 1 slash root n plus 2 sort of a bound is typed. So we put that on the, I'll put that on like the homework set. Yeah. Okay. So let's try a different problem now. Yeah. Okay. Here's a question. Okay. So we have a complete graph. Kn. We label its edges. One, two, up to, and choose two. Where no label is repeated. Okay, prove that. There is a trail. I'll define what a trail is. I'll just complete the question. Of length n minus 1 with increasing labels. What a trail is this. So in a graph, if you've seen what a path means, a path is just a set of sort of distinct vertices in a line, right, where no vertex is repeated. But in a trail, we're allowed to repeat vertices, but we're not allowed to repeat edges. So for example, so think of this as like a path which goes like this. So the graphs are, the edges are not directed, but I'm just imagining I'm sort of traveling along the vertices like that. And so in a trail, I'm allowed to do something like this. I go from here to here, then here, and then I go here, and then here, and then here, and then here. So in a so in a path, we cannot repeat vertices. In a trail, we may repeat vertices, but we cannot repeat an edge. And then there's a more general version where we can repeat edges as well, which is called a walk. So we have a trail. So yeah, so we need to show that there's a trail of length n minus 1 with increasing labels. Tricky. Yeah.
The labels are already, the edges are already labeled. No? We have proved no matter how they are labeled, it holds.
Yes. Just a note in the previous problem, if you know about something called affine planes, then it's sort of related to that, the construction. So if you want to know about the construction immediately, then you can look into what affine planes are. But I'll try to put a problem where so we get some sort of a closure that this is optimal. So, but yeah, let's come back to this problem for now. Give me a minute, I'll be back. So when I say increasing labels, I mean I'm traveling along the edges so that the labels are increasing. And the length is the number of edges, not the number of vertices. Oh, okay. So it, oh, I don't think I need the assumption that no label is repeated. So yeah, I don't think I need that assumption.
So then the labels can be equal as well. Would that also be increasing?
Yes. By increasing, I think I should clarify that I mean non-decreasing. Also, really, the labels 1, 2, and choose to don't matter. I mean, you could have taken any natural number as a label because there are only and choose two edges. So taking instead of all naturals and taking only 1 through and choose 2 is the same thing because I could just scale it down so that inequality, equality is the same even now. So um, Just as a reminder, what was done in the class yesterday, if there's someone who attended, um, yeah, PHP, but did you cover something of the sort of air Descarado theorem or something of that sort, where you have a sequence of mn plus one integers, there is an increasing sequence of m plus one or a decreasing sequence of n plus one, sort of a theorem?
Erdos theorem something.
Yes.
Yeah, Adosh Carroll.
Yeah, he stated the
Oh
theorem.
yeah,
But
air Descarado is different. Yeah. Okay.
yeah,
I see. So, okay. So let me just give a hint here. So, so for uh, so for any vertex v, let us define some weight w of v to be the length of the longest path or longest trail ending in v, ending in or at whatever. Yeah. So we need to show that there is some v for which wv is at least n minus one. So note that it suffices to show summation of wv is at least nn minus one. Because then by pigeonhole principle, at least one of them will be at least n minus one. It's somewhat similar to the idea of the other theorem, where to each index we assign a pair of numbers. If you've seen the idea before, but yeah, you could use this hint anyway.
I really didn't get the definition of thing, like WV.
Okay, so for okay, so be defining it to be the length of the longest trail that ends at that vertex. So that is, let's say we have some sort of a complete graph, and we have some labels, whatever, 1 through 10, yeah, and consider this p. So maybe there's a path. Okay, longest trail, longest increasing trail is what I should say. Um, Non-decreasing trail ending at v. Yeah. So maybe this is the longest. Um, maybe this is a long. Maybe say if um, this is 5 and this label is 6, then this is a non-decreasing trail of length 2. But maybe this is also 5 and then this is also 5. So then I get another trail of length 3, and then perhaps this is 7, and then this is 8, and this is also length 3, but maybe this is 7 and this is also 7. So then I get a length 4 trail, etc. So what's the longest trail I could find which ends at v, right? So that's what w of v is. So I want to so if I can show that the longest trail overall has length at least n minus 1, then I'm done, right? It's equivalent to the problem, right? Saying that there exists a trail of length n minus 1 is the same as saying that the longest trail has length at least n minus 1. So I want to show that some wv is at least n minus 1. But even if I can show that the sort of average is at least n minus 1, even then I'm done, right? Because then the longest would be at least n minus 1. So I can cut it midway and make the length exactly n minus 1. Does that make sense?
Yes.
Okay.
Can I If there are two edges that share a vertex can't have the same WV, right? And then I don't know.
I'm sorry. Why is
Two
that
edge
so?
because if they have the same, we could always add the other one, whichever one is bigger than the other. We could always just add the other one. Wait, no, I'm
Uh,
really wrong. No. I was getting
yeah.
confused.
Mhm. So just to make sure, trail can repeat vertices but not edges. So just to make sure. Uh, so we want to show there exists a V such that WV is at least n minus one, and that's the same that is implied. I mean, this happens if it is true that the average of WV is at least n minus one, and in fact, this will be true. So the idea is to show this, and so this is sort of like the PHP part of it, right? This is really PHP. It's sort of like a weighted PHP, right? If the sum of numbers is some S, then at least one of them is at least equal to the average, right? Sort of obvious, but that's really what widget rule is. Okay, so we want to show this now. Let's keep it of this form. Let's keep it like this. Maybe it helps to notice that this is equal to 2 times the number of edges. Maybe if that does, maybe if that helps somehow, who knows?
Isn't like we show that every edge is in some longest trail of some vertex? I mean, longest trail of some vertex.
Uh, Longest trail of some vertex is defined by
I mean, the WE, no, is the length of the longest non-decreasing trail ending at V.
every edge is a part of the longest tail of some vertex. Um, but that would, even then, it would just show greater than equal to m, right? Even if you try to use that, it wouldn't show up to m anyway.
Why, like every edge is in some, no? So there are
Because
like
there are
two.
m edges, right?
Oh, yeah.
Yeah.
Okay. So basically, in trail of two vertices.
You could try that, or maybe something else. I'm not sure. I'll have to think about it. Um, so maybe consider the following graph for a counterexample. Maybe I only 5 vertices. If this has 1, 1, 1, 1, and 3 and 10, or not 10, whatever, 6, or 4, whatever, or maybe 2, 3, doesn't matter. So the longest trail ending in C is I mean it's 1, 2, 3. So yeah, not exactly this. Maybe I need 5 vertices for a counterexample. So okay, yeah, I think this should work. So yeah, I don't think CD occurs as an edge of any maximum trail among all V. Yeah, I think this should work as a counterexample to your claim. Basically, I've made any edge joining C and any of A, B, E to be 1, and D and any of A, B, E to be 1, and then I've made A, B, B, E, A, E to be 2, and C, D to be 3.
Yeah. Fine.
Yeah, so the maximum ending at C looks like A, E, E, B, B, A, A, C, or something of that sort. No, this doesn't quite work. Wait, maybe I should, uh, maybe I should swap the labels.
No, like in C, ending in C would be C A D B C. That's longer than 1 3.
Maybe this. Yeah, I'm sorry.
The longest ending in with the earlier word or earlier labeling. I'm saying 1.
Oh yeah,
One.
true. So that would have worked anyway.
Also, the one which you draw later wouldn't work because then 2 3 items. Oh no, wait.
That would also work, I think. Because
This also
AE.
works. No,
Yeah, this also works. Yeah.
no. I mean, 3 comes in the longest trail of D. C A
Uh,
D B C D.
you can't go from C A D B C D, right? Uh, you're right. Wait, then I need to think of something better. uh, I mean, your claim might be true. I just feel like it's false. So it might still be true that every edge occurs in some at least 2 trails. In fact, I don't think this labeling is good. So, maybe something of this sort. Let me go back to this.
This is like take A B E, then you repeat the same thing. C B D A C D. Shall I repeat again?
True. Mhm. Right. Uh, mhm. What about this? Uh, can we? Um, what about CD now? I'm just thinking about that. Does it occur in? Uh,
You can take like B, A, E, B, C, D. Oh wait, BC is 4.
no, we can't do it. Yeah, like that. Yeah, that doesn't work. We can't use a for if we want to end at D, we cannot use CD because how would we have come to C then, right? So definitely a trail ending at D does not use CD. Maximal, that is maximum. It's fine.
Yeah, sure,
Uh,
but CD does come in the trail of A, let's say. B, A, E,
yeah,
B, B, C, A.
that did not use CD.
B, A, E, B, D, C, A.
Oh, uh, mhm. But isn't BAEB DECA better? Isn't BAEB DECA better than what you said?
Ah, yes.
I'm just thinking about it. So yeah, I mean, it could still be that CD is used. Just thinking about it. Suppose I want to use this edge somewhere, right? Then it better be like DC, right? It cannot be like CD because then unless we start from C, but then we cannot proceed. And I mean, I want to end at A, right? So it cannot be CD because then all other edges are 2, right? So it must be DC, and then since everything is 4, I must end at A. So the ending should look like this if I want to use CD and end at A, right? So
Yeah.
it must be like this. But then how did I come to D? Many ways.
D, E, C, A is better. Yeah.
Uh, no, I mean, maybe I've used DE somewhere else, right? That's always possible.
Ah, yes. But I mean, if you use, then there is 4 only, no? So you cannot use it DE elsewhere, I guess.
But I could do E, B, A, E, D or something, right?
But that's smaller, I guess.
It's the same length, just this.
You have written D 2 times, no?
That's okay. Oh,
In the
sorry.
other one.
Oh, yeah, you're right. Mhm. These are 1, 2, 3, 4, 5, 6, 7 edges. Yeah. I want to use 5 more edges here. Which I don't see what to do. Wait. I must use the ones first and then the twos, but that's not exactly possible. Or is it? Yeah, I don't see how to do it.
Maybe the flame is false.
Yeah, perhaps. Hmm. Let's just keep this example. Okay. Yeah, coming back to this, right? We want to show this. Just to recall from coming back from the diversion that we said that for any vertex we define WV to be the length of the longest non-decreasing tail that ends at V. And we want to show that there is a V for which WV is at least n minus 1. And we're saying that if we show that the average of WV across all V is at least n minus 1, then we're done, right? And how do we do that? Just copying sort of the essentials here. Where this is the definition. Right? Okay. So we are here right now. So this sort of so what I'm trying to hint here is that maybe the thing is true for general graphs on M edges. Maybe this thing is true that for M edges I can show that that the average of WV is at least 2M by N or something of that sort, right? That's what I'm trying to hint at. So is the average of WV at least 2M by N for general graph G, simple graph G on N vertices. So forget complete graphs. Can we sort of generalize and show that this is true? maybe we could induct on the number of edges or something. So what I'm trying to say here is that suppose G has n vertices, m edges, and we can define everything as before, right? The longest non-decreasing trail, where we label the edges from 1 to n choose 2, and I'm asking whether it is true that summation WV as V ranges among the vertices of G is at least 2m. Is this true? Because if this is true, then we're done, right? Because for a complete graph, we have n choose 2 edges, so we're done. Yeah.
I don't know if this would be useful, but like 2m by n is like the average degree. And
True. Yes, it is
so,
true.
so like the average of WV is like greater than the average degree.
Yes, that is true. I did try to think about it in that way. I wasn't able to make much progress in that direction, whether we could sort of directly prove that the average weight and the average degree are related. But what really helped actually was to sort of induct on M. So that's what really helped me. But yeah, that's a good observation. That we're saying that the average of WV is at least as much as the average of DV. But yeah, I'm not sure how to exactly relate the two together.
Also, like even if you induct, the idea will be if there are, let's say, m edges existing, we add one more edge, and then it becomes greater than 2m plus 1. Something of that sort will be induction,
2m
right?
plus 2. Yeah. 2 times m plus 2.
Two times, yeah.
Yeah. Yes.
So doesn't that prove my claim that every edge is in two trails, kind of?
Uh, um, it could. It might be true. It might still be true. It might still be true in that graph, and we're not making the correct observation.
Yeah.
So yeah. So it's not okay. So let's try the problem, and then we'll discuss what you were trying to say, and we'll see uh, how the two are related or where there's a flaw, if there is any. Yeah. Okay, so basically the point is that if we do this, then maybe the addition of an edge makes new longer trails that makes edges which the older edges no longer participate in two trails. Does that make
Yes.
sense? Yeah, that could be. Yeah. So I have the boil water notice here, which was like the water treatment plant here was not working. So I had to buy bottles from the shop. And so I'm thinking bottled water right now.
So did IIT Bombay give you scholarship, or like you have to apply it um, separately?
Uh, I mean, I have to apply it separately, but maybe we could keep these questions at the end of the session. I'll stay back to answer these. So, what would the idea of induction look like? So, I'm trying to induct on M. So, we're trying to induct on M.
And the n is fixed.
The N is fixed, yes. So, we're sort of just adding an edge, right? We're adding edges one by one.
But we don't know the label, right?
True, but you could keep the label as you can sort of just think about deleting edges, and so keeping the label as the same as the label here of the edges that we're looking into. So uh, sort of like an induced subgraph, right? So um, so think about it like this: we um, we want to show the statement for some graph, and we just delete an edge and then change that by induction. There is the sum of weights of this is at least 2n minus 2, and then we bring back that edge and then show that the weight has increased by at least 2. Does that help?
Yes.
Okay.
Oh, so is it like we have to show that this increases by 2? So now we consider the new edge added, the new vertex added, and we show that the trail of it,
Vertex added,
I mean, edge added, sorry.
edge added.
The
Yeah.
Oh, it can be added between two existing vertices also. Fine. I was thinking like if I mean, among the n edges, the existing vertices are between suppose n minus 1 vertices.
Not sure what you mean because
I
we're
mean, like,
keeping n the same, right? We're just adding one edge. We're not
yeah,
adding n minus one edges. Yeah.
yeah. Can you draw like A, B, C, D for vertices as of now?
Okay. So A, B, C, D. Sure.
Suppose the existing subgraph is AB and BC edge. Let's say this much.
Okay.
So now the one vertex is free, no, D.
Okay.
So now my idea was if we add one edge to D, like
Let's
let's
say
draw.
BD.
Yes. So if you show that the trail of D is of length at least 2, then that
I mean, does
induction.
it's a at least 2 is not necessary, right? Because I could have 4, 4, 3 or something. But maybe it affects the length of 3 of B, but although it doesn't, right?
Oh, yeah. If it's the minimum, like the only way it cannot be of length 2, the trail of D, is that it's the minimum length, minimum weight.
Not necessarily, because I could have had something like this, which is 1, but then these are 4 and this is 3, right?
Yeah.
So BD is the new edge added. So 1 is the minimum, but we only add 1 to D. Yeah. So maybe think about carefully choosing how these edges are being added one by one. Or carefully choose which edge you're deleting from G and then calling the induction on. So basically, if my graph was like this, A, B, C, E, and then this is 1, 3, sorry, 4, 3, 4. Then W of E is 1, W of A is 2, W of B is 2, W of C is 3, W of D is 1, I think, right?
Yes.
I
Yeah,
think
and
deleting like the heaviest edge will like give
good. Yes, exactly. We delete the heaviest edge. Delete any heaviest edge. Yes, that's the idea. Suppose I delete this. What are the labels become now? It's 1 and 2 and 1 or something. That this is 1 and 1. And why is it that if I add the heaviest edge, then the sum of the weights increases by at least 1? So, so let me write down what I said so far. We want to show the claim is true for this, assuming that the claim is true for m minus 1. We know the base case m equal to 0 is true, right? So delete a heaviest edge. I'm using A because there might be multiple. Edge UV by induction summation of, okay, I should write W prime V because I'm talking about the new graph G prime, which is after deletion. So among V is at least 2 times m minus 1, right? And now I add this edge UV. So I had some graph G and I have UV and I add the heaviest edge, a heaviest edge. What does that do to the weights?
We have to show
Why
it
does it?
increases by 2, no?
Yes, we want to show that the total sum increases by 2 by adding this edge. And yeah, why is that so?
I think like you can consider the trails which are ending at U, and then they'll
Okay.
increase by 1, and then you can consider like the trails which are
Oh, why is that true? So suppose I have a trail ending at U, which is the longest leg that has length some L. Why does adding UV and say I have a trail ending at V, which is length, let's say LU and LV, and I've added this edge. What does it do?
and it would it's an increase in trail because UV is like the heaviest.
But now if I add UV, then it's no longer ending at U, right? I want to increase WU. Also, by the way, this is W prime. It's the same thing. This is W prime because that's the definition of W, right? But if I add the edge UV, so suppose I have a trail ending at U and I add the edge UV, then now it ends at V. But I wanted it to end at U, right? So that's changed exactly. So
Well, even like the WV prime thing would end at you. Okay, this is wrong.
okay, yeah.
If W
Uh,
prime V and W prime U aren't equal, then one of them will be bigger than the other, and then we're done. But if they're equal,
okay, so suppose W prime U is greater than equal to W prime V. Then what happens? Why are we done?
oh,
If I'm
if
strictly
W
here.
prime U is bigger than W prime V, then it's we can replace the longest one for V with U and then UV.
Okay, so we're saying that the trail starting from, let's say this is AU and this is AV, then this or whatever. Sorry, rather I should say let this trail be TU prime and this trail be TV prime. Then if WU prime is greater than WV prime, what we can do is we can consider this trail and then go here, and that's a trail ending at V that has length WU prime plus 1, which is at least 2 more than WV prime, right? So then adding, so that then rather appending UV to the trail TU prime gives us a trail ending at V of, sorry, I'm just writing at the very corner, of length WU prime plus 1, which is at least WV prime plus 2, right? So then that means we've increased the length of the trail ending at V by 2 at least. And all other the weight will remain at least as much, right? Because the graph is a super graph of the original thing. And so we've
Oh, and
increased the sum by at least 2.
okay,
Yeah, and if what about if they're equal?
then both increase by 1. Okay.
Exactly. Yeah. So if both of these trails have so so yeah uh, yes, if both of them have the same length, then both of them can be increased by 1, right? By adding UV. So then PU prime followed by V has the length of this is equal to W V prime plus 1, and the length of this trail is WU prime plus 1. So both increase by at least 1. So if they're not equal, then one of them increases by at least 2. And if they're equal, then both increase by at least 1. And so the overall weight has increased by at least 2. And we're done. Right? So
Yes.
is it clear? Okay. Yeah, and WU prime less than WV prime is the symmetric case. So just append VU to WV prime.
What
So
was
we're
the
done.
extremal part here? What's the
To delete the heaviest edge, right?
I see.
This is important, right? I mean, it sort of seems like in the grand scheme of things, this was a very small part, but that's how things work, right? It's always a mixture of arguments. So we sort of went through everything that is seen in general combinatorics. We went through PHP, and we went to the fact that often to induct, we have to generalize. So if you've seen some problems of this sort before, often so if you've seen of something of the sort 1 plus 1 plus 1 fourth plus 1 ninth plus less than 2, then you can't directly induct because it just won't work, right? So plus up to 1 by n square is less than 2. It won't work directly, but sometimes you can sort of make the argument stronger and suddenly induction works. So if you want to show that this is true, then induction works. So it's weird that induction works to prove a stronger statement, but doesn't work to prove a weaker statement. So we did something like that. We sort of made the question more general by talking about M instead of just the complete graph, so that we could apply induction. And then inside the induction, we could not have just deleted any edge because the argument doesn't go through. So because we can't just append UV. The whole point is that since UV is the heaviest edge, we can append it to any trail which exists in the graph G prime, right? And so that's where we used heaviest. So it's a mixture of a lot of things here: extremal argument, PHP, generalization, and reduction. Yeah. So
Also, is this WV idea like common in combinatorics problem? Or like
yes. So yeah. So sort of giving such weights is like quite a common idea. In fact, there's another proof for Mantle's theorem, which is like it's this question that if a graph has n vertices and no triangles, then it has at most n square by 4 edges. So there is a proof of that using this. So I'll put that in the assignment set as well. So yeah, so talking about weights is quite a general idea. In fact, even in that Erdős theorem about mn plus 1 sequence, there is an idea like this. We look at like the length of the longest non-decreasing subsequence starting at something and non-increasing starting at something. It's yeah, there are ideas. These sort of ideas do come up. By the way, I don't exactly remember both of them. I think it's Graham and I think it's this. And this question was answered by them. Yeah. Okay. Let's try another problem. Let's see what problem to try. Maybe people have seen this. Okay. Okay, let's try it anyway. Okay, so okay, so okay, so we look at what is called a chromatic number for a graph. So let me define that. So let's say we have some graph, and drawn it to be planar, but it could have been any graph, but it's okay. And we want to color the vertices of this graph in such a way that no two adjacent vertices are the same color, and we want to use the least number of colors possible. So what's the least number of colors possible is called the chromatic number. So chi of G is the smallest natural number k such that there exists a coloring of the vertices of G using k colors. This is at most k. I don't need to use exactly k, but it's okay. Colors such that for all UV in the edge set of G, colors of U and V are different. So sort of think about two adjacent vertices to be enemies of each other, and we're trying to form groups such that no two enemies are in the same group or something. And we want to form the least number of groups possible. And so that's the chromatic number. So what would the chromatic number here be? So, okay, so let's label this blue. Then clearly this has to be different from blue. So let it be red without loss of generality. And so this has to be different from both blue and red. And now notice that this vertex has to be different from all red, blue, and white because it's adjacent to all three. So let this be green. And then apparently this just works. This works, right? So the chromatic number is 4. In fact, we sort of showed that it is exactly 4, not just at most 4. In fact, it can be shown directly by noticing that this A, B, C, D here forms a complete graph. A, B, C, D is a complete graph on 4 vertices. So we need at least 4 colors. And so the chromatic number of this graph is 4. So that's what chromatic number means. Okay, so if you've not seen this before, let me put this problem as well. Let delta be the max degree of a vertex in G. Prove that chromatic number of G is at most delta plus, I should write it delta G, at most delta G plus 1. But now there's another problem. This was given by I think Edish was involved. Maybe there's also Edish. Not entirely sure. We want to show that this is at most 1 plus max h subset of G of delta h, where this is defined as min degree of a vertex in G. So let me know if there's a part in the second problem that is not clear. The second problem is stronger than the first problem because small little delta of h can never exceed capital delta of G, if you think about it. And so this is stronger than the first problem. So any ideas about the first part? Have you seen this before?
You can just start at a vertex and then just color it differently, right? Just keep going. Right?
Yes. Yeah, essentially. Yes. So the idea is that we can sort of just pick vertices one by one in any order and just color them using the least index that we can color. Think about colors as numbers, right? Let's say blue is 1, red is 2, white is 3, green is 4, etc. And so we can just pick any vertex and color it using the smallest index that we can color it with. So the idea for this is think of colors as numbers, naturals. Which means it's just equivalent to assign numbers in such a way that no two adjacent vertices are the same natural number. We want to minimize the largest natural number we are using. It's really the same thing, right? And um, and just go through the vertices in order, in any order that you want to. In some arbitrary order. Sometimes it's good to know the difference between arbitrary and random, but it's okay. I'll just avoid that discussion for now. Go through, we've given some arbitrary order, and for each we encounter, assign it the natural, which is assign it the smallest natural possible. Smallest natural possible, right? So basically what I'm saying is, um, let's look at this graph itself, right? So so let's remove the colorings and just think of colors as naturals. And just add that edge back. Oops. So let's start with let's go alphabetically, right? So this is 1, and then now look at B. 1 is already used up by some neighbor, so we'll put 2. And so now look at C. 1 has not been used because A is not adjacent. So just put 1. And then D, 1, 2 has been used. So then, sorry,
CA
1
is it?
yes, you're right. So 3. And then I'll look at D. And 1, 2, 3 have been used. So 4. And look at E. I can assign it 1. And then look at F. I can assign it 2.
I have one
And that's
doubt.
it, right? Yes.
It's basically like some sort of greedy algorithm, but how do you ensure that this greedy algorithm is optimal? It's not necessary, right?
It is not, which is why we've written less than equal to, right? We've not written equal to. If it was
So
optimal, then so the chromatic number can be strictly less than delta of 3 plus 1. In fact, it is right. Take any bipartite graph. Delta G can be arbitrarily large, but the chromatic number is at most 2.
yeah.
So this is just an upper bound. It's not optimal by any chance. And the reason why it works is that if we consider any vertex, then there are at most delta of G neighbors, right? So then
Yeah.
at least one of the first delta plus 1 natural numbers should not have been used by some neighbor. And so we can assign it one of them. And that's the
Okay.
logic. That's literally why the proof works.
So this is basically not the most optimal part, but this works for what the bound you gave.
Yes, but this may not be true. In fact, it is true that del chromatic number of G is equal to delta G plus 1 if and only if G is a complete graph You can try to prove it. It's a little longer, but or an odd cycle. This is called Brooks theorem. It might be Brooks with an apostrophe after. I'm not sure if the name is Brooks or Brook. So, whatever. Yeah, so in fact, delta G plus 1 is only achieved for odd cycles where the degree is 2 and the chromatic number is 3, or for a complete graph where the degree is n minus 1 and the chromatic number is n. And for everything else, in fact, the chromatic number is at most the degree, the max degree.
What do you mean by G to be an odd cycle? Do you mean that an odd cycle exists in G?
No, just literally an odd cycle, like this. It is an odd cycle, not
Okay.
contains an odd cycle. Yeah,
Okay.
that is. I'm saying that. Yeah.
I have a doubt. Like, so you're taking a subgraph of like G,
Yes.
right? H is in
Yes.
subgraph of G, but then you take G only, no? Like you take H to be G.
Okay.
It's still fine.
But the smallest degree in G may be much lesser than delta G.
Yes, I see.
Yeah. So it is true that delta H is at most capital D of G for all H that are subgraphs of G. I mean, generally, okay, let me use a subset notation, not the lesson notation. Subgraphs of G, but it may be true that that for any such subgraph, little delta H is strictly less than capital delta G, in which case the second thing is a stronger bound, right? So
How is that possible? Because like you wrote the definition of delta H as minimum degree of a vertex in G. So like the degree you're considering is in G only.
in H. So sorry. In H. Sorry.
Also, like
Yeah,
H is any subgraph, no?
any subgraph. I mean, it suffices to consider induced subgraphs, but yeah, any subgraph.
Yeah. Okay.
It doesn't really matter because if you take a max, then only induced subgraphs matter.
What do you mean by induced subgraph?
Let's avoid it. Let's just say any subgraph.
Sure.
An induced subgraph is like you take a subset of vertices and take all edges. For example, if I take A, B, A, D, F, then in an induced subgraph, I must take AD and DF as the edges because they're also present in G. But in a subgraph, I may choose to omit edges as well. So this is a subgraph, but it's not induced. So basically, in a subgraph, I can take a subset of vertices and a subset of edges. But in an induced subgraph, once I've taken the subset of vertices, I must take all edges that are present between those subset of vertices.
Yeah, got it.
Yeah. And so the point is that really only induced subgraphs matter.
Yeah.
Shourya, maybe try to wrap up.
Yeah, I'll wrap it up in. Okay, so maybe we won't have time to prove this. How about I'll put in the assignment set as well, and I'll try to divide it into parts where you can try to prove each sort of a sub part and then combine them together to prove this. It's a really nice theorem, by the way. I'll also, it's not exactly extremal combinatorics, but I'll try to put, I mean, it's not hard, it's a little hard. So I'll try to give hints for this and I'll put up more extremal problems that have appeared in Olympiads as well. The point is, I know some of you might be thinking that these are not exactly Olympiad questions, but always the sort of ideas in Olympiads come up like this. So, for example, I really like this question because it sort of combines all ideas that come up in combinatorics, right? So, induction, extremal argument, PHP, generalizing the question, even though sometimes that might seem absurd. Yeah, questions? Hopefully, none of these questions you've seen before. This first part I put just to emphasize the fact that the second part is stronger. This is sort of famous in some sense. Okay, yeah. Questions, please.
I can end the recording, right?
Yeah, I think so. Yeah.
Sure.
How do you remember so many names?